Good afternoon, everyone. I'm Malamay Ronquillo, and I'll be discussing about thermocouples. So first, let us define what a thermocouple is. A thermocouple is a sensor used to measure temperature. Thermocouples consist of two wire legs made from different metals. The wire legs are welded together at one end, creating a junction. This junction is where the temperature is measured. When the junction experiences a change in temperature, a voltage is created. The voltage can then be interpreted using thermocouple reference tables to calculate the temperature. They are typically selected because of their low cost, high temperature limits, wide temperature ranges, and durable nature. When two wires composed of dissimilar metals are joined at both ends and one of the ends is heated, there is a continuous current which flows in the thermoelectric circuit. If this circuit is broken at the center, the net open circuit voltage is a function of the junction temperature and the composition of the two metals, which means that when the junction of the two metals is heated or cooled, a voltage is produced that can be correlated back to the temperature. Thermocouples are the most popular type of temperature sensors. They are used in diagnostics testing for vehicle engines. Some gas appliances such as boilers, water heaters, and ovens use them as safety features. They are also used as an aid in milk pasteurization and as food thermometers. In industry, they are valuable as probes and sensors. Thermocouples are used in many industrial, scientific, and OEM applications. They can be found in nearly all industrial markets such as power generation, oil or gas, pharmaceutical, biotech, cement, paper and pulp, etc. Before discussing the various types of thermocouples, it should be noted that a thermocouple is often enclosed in a protective sheath to isolate it from the local atmosphere. This protective sheath drastically reduces the effects of corrosion. There are many types of thermocouples, each with its own unique characteristics in terms of temperature range, durability, vibration resistance, chemical resistance, and application compatibility. Type J, K, T, and E are base metal thermocouples, which are the most common thermocouples. Type R, S, and B thermocouples are noble metal thermocouples, which are used in high temperature application. Type B thermocouple is used in extremely high temperature applications. It has the highest temperature limit of all the thermocouples listed above. It maintains a high level of accuracy and stability at very high temperature. The Type E has a stronger signal and higher accuracy than the Type K or Type J at moderate temperature ranges of 1000 degree Fahrenheit and lower. The Type J is also very common. It has a smaller temperature range and a shorter lifespan at higher temperatures than the Type K. It is equivalent to the Type K in terms of expense and reliability. The Type K is the most common type of thermocouple. It's inexpensive, accurate, reliable, and has a wide temperature range. The Type N shares the same accuracy and temperature limits as the Type K. The only difference is that Type N is slightly more expensive than Type K. Type R is used in very high temperature applications. It has a higher percentage of rhodium than the Type S, which makes it more expensive. The Type R is very similar to the Type S in terms of performance. It is sometimes used in lower temperature applications because of its high accuracy and stability. The Type S is used in very high temperature applications. It is commonly found in the biotech and pharmaceutical industries. It is sometimes used in lower temperature applications because of its high accuracy and stability, just like Type R. Lastly, the Type T is a very stable thermocouple and is often used in extremely low temperature applications such as cryogenics or ultra-low freezers. The working principle of thermocouple is based on three effects discovered by Seedback, Peltier, and Thomson. The first one is the Seedback effect. It states that when two different or unlike metals are joined together at two junctions, an electromotive force is generated at the two junctions. The amount of EMF generated is different for different combinations of the metals. As per the Peltier effect, when two dissimilar metals are joined together to form two junctions, EMF is generated within the circuit due to the different temperatures of the two junctions of the circuit. The last one is the Thomson effect. When two unlike metals are joined together forming two junctions, the potential exists within the circuit due to the temperature gradient along the entire length of the conductors within the circuit. In most of the cases, the EMF suggested by the Thomson effect is very small, and it can be neglected by making proper selection of the metals. The Peltier effect plays a prominent role in the working principle of the thermocouple.
Hello everyone, it's Cosmo Casper, and today I'm going to be showing you how to test a thermocoupler with a meter. This is actually really simple to do, and you might have seen my other video where I actually used a thermocoupler tester, but then I realized my channel's about electric, so why not show you how to do it with a multimeter? So the first thing you want to do is go to your volt setting, and you want to be on DC milliamps. So I'm going to click that. You can see the symbol changed to DC, and it says, sorry, I just said milliamps, it's millivolts. You see MV right there, it's millivolts. Now, just my meter being in open air, like if I touch it and stuff, you're going to see these numbers change. Don't worry about that. Once you hook it to the thermocoupler, it should steady out at 0. You're going to take the common ground, the black lead, hook it to the copper of the thermocoupler. Then you're going to take the red and hook it to the top, and you can see it zeroed out real quick there for me. And then all you do is you take heat and you apply it to the thermocoupler. And you should see numbers being generated. I'm generating 4 point, 5 point, 6 point. Basically, I'm making millivolts. And what this actually does, the millivolts are what powers the internal workings of a thermocoupler. Like this right here is a hot water heater control. You can see if I press this button, the button is actually lined up perfect, with where the thermocoupler would normally go into down here. So when I press that button, this is the internal piece, this goes down and makes contact, and it stays depressed, which lets the gas flow through the inlet. Basically, if you press your button down on your controller or your furnace, whatever you're working on, and it's not staying depressed when your pilot's lit, you probably have a bad thermocoupler or a bad control. That's a really quick, easy way to diagnose this. So this is the internal piece. Not sure how good you'd be able to see this, but how it works is when those millivolts are generated, it powers this little coil in here, which makes magnetism, and that's actually what holds this down and lets the gas flow. So when a thermocoupler is not producing millivolts, it basically will not hold down the internal coil of the thermocoupler control. That's the best way I can describe that to you. You saw my other video, you can actually buy these thermocoupler testers where instead of looking for a millivolt reading, you just simply see if it holds the valve down. That's a more foolproof way of doing it, but the way you do it with the meter, stupid simple. You just hook it up like I just did, and you see if it's generating millivolts. Thanks, guys.